So for graph, we're going to talk about three things, just like we did for trees. So first we need to define what a graph is, and then we need to look at how we can traverse a graph. And finally, we are going to look at algorithms that make use of these traversals in order to do certain processing on the graph. Now, the main purpose of using a graph is to store data that in the form of relationships. So it means that the key information that you want to retain is the relationship between different objects. Now, for example, so let's say you want to represent data that has the form of a transportation network. So in this case, you want to store the connectivity between different stations. So in this case, the stations are the objects or the vertices, that's what we call them. And the connection between any two stations, whether they are directly connected to one another, are what we call edges. Now, based on this kind of representation, you can then investigate problems such as whether you can go from any particular station from another station, and in what is the fastest way, or what are the possible ways, and so on. Now, other than transportation, it could be land, it could be air, because you can imagine airport, right, in terms of different hubs that the flights are going to connect to. Now, we also use graph to store networks of people, for example. Now, this is an example of the connections between the attackers that happened in 9/11. There were then 4 planes, and the 4 planes, because it was a secret mission, so not everybody knew one another. So they are connected in a certain way that the communication had to go through certain connections. And they are then colored by the different planes that they were on. Now, here, by looking at the way that they are connected to one another, the analysts can then look at this and they can make inferences. For example, they can say, all right, so if we had known this beforehand and we wanted to prevent the attack, could we possibly take out some parts of the graph such that it will disrupt the communication? Now, so for example, if they had taken out this guy, let's say the red guy here, right? Then in that case, this part is going to be disconnected from the rest. They can't communicate anymore. So this connectivity structure is what is of interest when we talk about graphs. Now, we can also look at a network of people in terms of communication. This is a network that we built from Enron emails. Enron was a company that went bankrupt in the early 2000s. And the reason is because there was some fraud going on and they were trying to do investigations. And it's part of the investigation, they had to give up their emails, and then the analysts were looking at the connections between who sent messages to whom and who could be implicated in that particular case. This is another example, which is on Hollywood collaborations, whether actors are playing in the same movies together. Now, there are some interesting things that we can gain by studying the graph, and one of the graph properties that of interest to us is how well connected are the graph itself. Now, this is one interesting experiment that was done in the 1960s. It was actually done by a psychologist, not a computer scientist, and he actually wanted to know what is the structure of human connections. So he had ran the following experiment. So he had envelopes, right? So it was 1960s. So we are talking about hard, like an envelope. This is not an email. Now, in this envelope is addressed to a recipient in Boston, Massachusetts. So the name of the guy that is addressed to is there. And he went to 2 cities in the US, Omaha and Wichita, Kansas. And he distributed these envelopes. And the envelopes basically had an instruction. So if you receive one of these envelopes, what you're supposed to do is to pass it on to another person that you think can pass it on to eventually the named addressee. You're not supposed to just directly mail it. You're supposed to pass it on to one of your human acquaintances. And when the experiment went on, it turns out that some of these acquaintances in fact cross cities, and through a series of connections, eventually you go from Omaha, Nebraska, all the way to Boston, Massachusetts. He sent out about 300 of them. 60 eventually reached the recipient. And the others probably didn't follow the instructions and so on. But the surprising thing is that the average path length, means how many hops it takes to send messages from one end of the country to another, it's only 5 or to 6. And this gives rise to the term 6 degrees of separation. which encapsulates the idea that the connections, even within big graphs, are actually very short. And this has been established again and again, not just in terms of human networks, but also in terms of computer networks. So they are looking at, for example, what is the diameter of the internet network. At some point, the numbers was around 15 or 16. That means that when you're trying to send messages from one end of the world to another end, it probably jumps over only about this 15 servers before it gets to the final recipient. And the property of the graph that allows this level of connectivity is because of the imbalanced distribution of the way the edges are distributed. So some nodes are very highly connected and they become the hub where most of the messages are actually flowing through. All right, so now the idea then is how do we make use of this graph structure, not only to reflect the real world, but actually to do something useful with them. And that requires us to be able to transform what we think about connections in terms of something that a computer can process, which is a graph data structure, and ways to manipulate a graph in order to do something useful for us. Now, so first we're going to discuss what is a graph, and then we're going to talk about some properties of the graph before we talk about traversal. Now, this is the first example of a graph. We call the two main components essentially the vertices and the edges. The vertices are the objects. So for example, A, B, C, D, E, F, these are the vertices. Sometimes we call them nodes. So we consider nodes vertices equivalent. Then there are the connections. The connections between any two vertices, we call them edges. And sometimes we also call them links. So we consider edges and links to be equivalent. Now, when you have a set of vertices, you start to connect them. And in this case, there is actually a direction. So you look at the arrow, right? So there is A to B. Then there are, of course, other connections, B to E, B to D, B to C, and so on. Now, this graph, as it is actually meant for human consumption, because we can look at this pictorial representation, and we can make sense that there are things there and they are connected. But to a computer, this is just an image. They can't actually process the graph as it is. So instead, they need to transform it into something that is discrete, that we can process it. Now, what are those? So we call them representations. So it means that these are the ways in which the graph are stored. There are two main ways. One is called adjacency list. The other one is called adjacency matrix. And this case, these two are the same, are two representations of the same graph, which is shown earlier. Now let's take a look at how they are represented. So in the adjacency list representation, you have a list of vertices. So you have A, B, C, D, E, F. They are vertices. And for every vertex, you keep track of a list of their neighbors. So we say A adjacency list has B and C. And it has B and C because in the graph, A connects to B, A connects to C. So in that case, the list is going to contain the list of outgoing neighbors, neighbors that A can connect to. Now, the rest correspondingly will follow. So B has edges to C, to D, to E. So accordingly, we have B's list containing C, D, and E. C has edges to D and A, D to B and F, E to D, and F to nothing, right? Now, we can also represent exactly the same information, but in terms of a matrix. So in terms of the matrix, because you have 6 vertices, A, B, C, D, E, F, so you have a 6 by 6 matrix. On one side, the rows, they are the sources, the columns are the targets. So the particular cell is going to tell you whether or not there is an edge between the source to the target. Now in this case, we're going to use binary representation, zeros and ones. So 1 means that there is an edge, 0 means there isn't. So here A to B, A to C, they are edges, but A to all the other vertices are zeros, meaning that there are no edges from A to all the other ones. Okay. Now, once you have such representation, then you can pass it on to a computer algorithm that would then know what to do with the graph. Now, at this point of time, let's re-emphasize again, right? The important information in a graph is the connectivity. So when we talk about a graph, they are just vertices and the edges. There is no inherent ordering among the vertices. So it just so happens that we put them to be A, B, C, D, E. But in reality, in practice, when you try to store the graph in a computer, the vertices are not necessarily ordered in any particular way. So you could have it like C, B, A, F, A, for example, right? So the ordering is actually depending on the way that you are implementing it. In any other order, it's still valid as long as all the connectivities in terms of the edges and the vertices are still maintained. Okay? Now, there are some terminologies that we associate with a graph. One is what we call in degree, which is the number of incoming edges. So if we take B as an example, the in degree will be the number of things that go into B. So there is 1 from A, there is 1 from D, so that is 2. Now the out degree is what is going out of B, or out of a vertex. So in that case there are 3, right? So B goes to C, B goes to D, B goes to E. Now then we talk about a path. A path is a series of edges, right? A sequence of vertices that are connected by edges. So for example, A, C, D, F, that is a path. So A connects to C, C to D, D to F. And they are a sequence. So in this case, we call it a path that starts from A and it ends at F. And we call a path simple if it's unique. It means that there isn't any repetition in terms of the vertices within the path. So for example, A, C, D, F, everything is visited once, so that is a path. Now, we call it a cycle if there is a repetition. So for example, you go from A to B, B to C, C to A. So in that case, you have a cycle because it leads back to a node that you have visited before. So that's a cycle, right? Okay, now we were talking about directed graph. Now we're going to talk about the complement of it, which is what we call undirected graph. Now, undirected graph is different from directed graph in the sense that you don't see the arrows. So there are no directions indicated on the graph. So for instance, AB here, there is no arrow either way. Now, so we call it undirected graph, but the more correct way to think about this is not so much that they don't have directions, but actually they have both directions simultaneously. So when you see undirected graph, what it means is that A can connect to B, B can connect to A. So the connections is symmetrical, which means that in the way that we represent the graph, so from A we can go to B, and from B we can go to A. All right. Now, why do we need to have both types of directed and undirected? Because in reality, there are different types of graphs that we will try to store because they have different semantics. Now, for example, right? So let's say you're on Twitter, right? So we can try to store the connections of people on Twitter as a graph. Now, on Twitter, you follow someone. If you follow someone, does the other person necessarily follow you? No, right? So just because I know that you're following a celebrity doesn't mean that the celebrity is following you. So then the kind of relationship you have is something that is directed. Is one way, but it may not be the same the other way. Now, on the other hand, if you are using a graph to store, let's say, Facebook data, so on Facebook, you want to be friends with someone, you ask, right? So you send a friendship request, and it's only when the request is granted, right, it's approved, then you become friends with the other person. And in that sense, once you are friends with that person, in anything that you're doing, there is no difference, right? Whether A friends B or B friends A, they become friends. Now, in that case, there's an example of undirected graph. So depending on what you're trying to model, you either use a directed graph or you use an undirected graph. Right? Now, some of the things that we talk about in these slides, they are also explained within the reference materials. And there is also a Python lab there that talks about different graph implementations. So some of the codes that you see here would actually be implemented inside the Python lab itself. Now, so when we have a graph, the two things that matter are the vertices and the edges. So you should be able to add or delete vertex, and you should be able to add or delete edges. Now, because there is a visualization component within the Python lab, this specific implementation allows you to specify coordinates. They will place the vertex into some canvas. They can be visualized. but you can do it without that too if there is no intention to visualize it. Now, there is also the concept of weights, because so far we only talk about binary graph, just like ones and zeros, whether the edge exists or not. But sometimes you want to reflect the strength of the relationship. So then what you can do is that it's not just one or zeros, you can then attach some real numbers to the weights to reflect what is going to be the strength of that connection. All right, now, so far, any questions about graph in general? Now, every vertex has a label. The label is, when we say A, B, C, D, there's a label. It's what you call it. It's essentially some attribute of the vertex. And it has a list called adjacency list that contains pointers to the neighbors. Now, a graph itself, by itself, right, stores data. But to process it, to solve some problems with it, you need to have a way to systematically process information that is in the graph. Now, previously, we did trees. In the case of the binary tree in particular, there are 3 traversals: pre-order, post-order, in-order. And they are defined in terms of the relationship between the parent and the children. Now, in the graph, there is no such thing as parent or child. Any node can connect to any other node. Whereas in a tree, a parent can connect to the child, right? So what does that mean? It means that we cannot use pre-order, post-order, in-order, because number 1, there is no such thing as a parent. Number 2, there is no such thing as a left or right. So we have to define a whole new way of thinking about a graph, thinking about traversal. And we are going to have 2 main traversal methods, something that we call depth first search and something else that we call breadth first search. There are 2 different ways of processing the sequences of processing nodes in the graph. Now, before we go into them in detail, I just want to point out a couple of differences between the way we think of a tree and the way that we think about a graph. So number 1, so when we talk about traversal on a tree, do we specify where you start from? You always start from the root, right? So we never ask the question. You always start from the roots. Now, why do we start from the roots? Because on a tree, only by starting from the roots do you actually have a chance to visit every single vertex in the tree. Now, in a graph, first of all, there is no root. So all the vertices have equal standing, right? So they are just vertices. So there is no root. So which means that if you're going to do traversal, you have to specify a starting point. So you cannot say, I'm going to do DFS on this graph. You have to say, I'm going to do DFS starting from this node. Because if you start from a different node, you get a different sequence. Okay, so that's one. The second thing is that because from a graph, there's no guarantee that starting from any point, you will be able to reach all the other vertices. It's not guaranteed to happen. So which means that in a graph, you don't have expectation that a traversal will necessarily visit every single vertex. It will only visit the ones that are reachable from the starting point. Okay, so there are some differences between what is a graph and what is a tree. Now, let's then go on to these 2 traversal methods. I'm going to describe the algorithm, and then we're going to pause for some class exercises. Now, the first thing we're going to look at is what we call depth first search. So the D is for depth, the FS is for first and search. And we're going to define this recursively. Now, the algorithm is proceeding in actually more or less straightforward fashion. It just needs you to bear in mind that it's a recursive method. So you start from a vertex. So this is the starting point. So the original vertex that you put in is a starting point. You're going to visit that vertex, and then we're going to look at who are their neighbors. And then we're going to take each neighbor, and if the neighbor is not visited yet, we're going to recursively call on that neighbor. So essentially, it's a recursive method. Now, the closest thing I can tell you about this is close to pre-order, in the sense that pre-order will visit the parent first, and then you're going to visit the children in a recursive form, right? In this case, it's similar. You visit itself first, which you can think of as a parent, and then you go into the for loop and to visit all the neighbors. But there are differences, right? So don't assume they are exactly the same. Now let's take a look at an example. So you have a graph, so you represent it in terms of adjacency list. So the list is going to look like that, right? So this graph is going to look like this. So we're going to do traversal on the graph. We have to pick a starting point. And let's assume for the moment it starts from A. So if we start from A, then we're going to call this method visit A first. So A will be visited first. So the number there is a sequence. Then we're going to go to the neighbors of A, and we're going to take a look at the first neighbor, which is B. And then we're going to recursively call on B. So A calls on B, so then recursive, right? So then B is going to call on C. C is going to call on D. Now D will call on B, but B is already visited before, so it doesn't do a second visit. So instead it's going to move on to the next neighbor, which is F. So D calls on F. Now then F calls on, no, but F doesn't have any neighbors. So then F doesn't have any neighbors, so it will basically skip this whole part, and then it will return the recursion to the previous method that calls it, which is D. Now D has no other neighbors, so it returns back to C. Now C earlier called D, but it now has another neighbor A, but A is already visited first, right? So then we don't do it again, so C returns back to B. Now by now B has processed C, it will move on to the next node, which is D, but D was already visited, so then it doesn't do that again, so then we go on to E. So after E, E will visit D, but D is already visited, so E returns back to B, then B returns back to A, and A has no other neighbors because C is visited. So then we get the sequence, which is A, B, C, D, F, E. And that is a depth first search. Now, the idea behind depth first search is the depth, which is to look at the graph and pursuing it to as long as it can go deep into the graph. So in this case, for example, we start from A to B, B can still go on to C, to D, to F. So we are actually exploring it and just following the path, the edges, as far as we can. Okay? Now, let me repeat one more time for the DFS. So it works almost like pre-order in the recursive form. We visit the node first, and now visit a node, we're going to recursively call on each neighbor. So starting from the first neighbor. Now, which one is the first neighbor? The first neighbor is second neighbor and so on is going to follow the adjacency list. Because in this list, we have B before C, so then A will call on B first. So then recursively, B will then be visited, and then it will go on to its neighbors. And the neighbors of B, as listed here, is C, D, E, so it will go on to C first. Now, C means it will recursively call on C. Now, C has two neighbors, D and A, so recursively call on D. D has two neighbors, B and F. B is already visited, so it goes on to the next one, which is F. So then F has no other neighbors. F returns back to D, D returns back to C, C returns back to B. Now B can still go on because there is still one unvisited neighbor, which is E. So then B goes to E, and then E returns back to B, B returns back to A, and at that point of time, the whole sequence is over. Okay? So essentially is recursive way of traversing the graph. Just follow the edges as they are listed in the adjacency list, but we're going to do it recursively. Recursive means that once you call a method, you have to wait until that method is done, which means that the method is going to move on first and call on the next method and so on. Now, we are going to contrast this with the second way of doing this, which is what we call the breadth first search. Now, the breadth first search, so first I'm going to tell you the key idea. Then we're going to talk about how it's achieving it. The key idea behind breadth first search is to try to visit the closest neighbors first. Closest means that we can reach them within shorter hops. So, for example, right, let's take a look at this code, right? The code here is making use of a queue. Now, the queue is used as a mechanism to store which nodes have been visited earlier. Now, this is an example, right? So the same graph exactly as before. So we're going to explain it through the example here. Now, you're given an adjacency list, which is from this graph. So when you enter into this method, first you create a queue. So which means that the queue is initially empty. Now, when the queue is initially empty, then we're going to visit the first vertex, which is the starting point, and then we put it inside the queue. So at this point of time, the queue only has one vertex, which is what you put in, right? Which in this case is A. Let's say starting from A, we visit A, and then NQA, the queue only has A. Then we're going to go through this particular loop as long as the queue is not empty. And what we do here is to dequeue it, and then we're going to visit all the neighbors. And as long as there is any neighbor that has not been visited, we're going to visit it and then enqueue it. So we're going to repeatedly ask a neighbor, who are your neighbors? Let me visit them and enqueue them. So which means that starting from A, we dequeue A. A has two neighbors B and C, so they are visited, they are enqueued. So now the queue has B and C. So you dequeue it, you get B. Then B has three neighbors, C, D, E, but C was already visited. D and E not yet, so we visit D and E, we enqueue them. So we get C, D, and E. Next dequeue, we get C. C has no unvisited neighbors, so we move on. We dequeue D. D has one unvisited neighbor F, so we visit F, we enqueue F, we get E and F. Dequeue E, E no new neighbors, F no new neighbors, and the queue is empty. And at this point of time, we are done. Right, so the process is starting from a particular vertex, we are going to visit it and enqueue it. And we are processing it from the queue. Each time we dequeue one vertex, and then we visit the neighbors and enqueue the neighbors. Now, if we contrast this to the earlier one, which is DFS, look at the sequence, right? We're going to look at the sequence here. The sequence for DFS is A, B, C, D, F, E. So that is the sequence for DFS. The sequence for BFS is A, B, C, D, E, F. So number one, they visit exactly the same set of vertices. They don't visit any more, they don't visit any less. Okay, so they visit exactly the same number, but they don't necessarily visit the nodes in exactly the same sequence. Now, so here there is a difference in the sequence. So here is A, B, C, D, E, F. This is A, B, C, D, F, E. So E and F are not visited in exactly the same sequence. Now, the key difference is the following. So when you look at the BFS, what it tries to do is to visit the closer neighbor first. So let's take a look at this example. So let's see, if visit A first, right? The starting point is A, if visit A first, because A is a distance of 0 from A. Now, what are the next nodes that are visited? B and C. Why B and C? Because B and C are one hop away from A. So you can go from A to B, A to C in a single hop. Now, the next node that are visited are D and E. Why? Because D and E are two hops away from A. So to go to D, A needs to go from B, so A, B, D. To go to E, you can also go from B, A, B, E, right? So they are within two hops away. Now, then we visit F. So why F? F is three hops away. It's A, B, C, D, E. So it's going to go with A, C, D, F, right? So that's three hops away. So for the breadth first search, it's going to prioritize visiting the closer neighbors first, and then the further away and the furthest away. Whereas for the DFS, we are going to follow as deep as possible, which means it makes it possible for us to visit F before E, although F is further away, because we're going deep into F first before we had a chance to go and do E. Okay, any questions so far? This one will require a little bit of practice to get familiar. So that's what we're going to do. Yes?
Can I ask, just now you said that there was no order, right?
Yeah.
So how would you know that C come first or B come first? Wouldn't the result be different, like especially in terms of DFS?
So whether it's BFS or DFS, in both cases the results are going to be different. So once the adjacency list is defined, it will follow the sequence that is in the list. So for example, it says that I is in the range of this, right? The length of the list, it will go from 0 to n minus 1. So if your list is like this, C, D, and E, is going to do C first and then D and then E. Now, that means the difference is not in the BFS or DFS, the difference is in how you construct this list. So when you have a graph, you need to first construct the list. Now, you can have different ways to construct the list, because in a graph, the ordering of the vertices is not important. But once you have constructed the list, then there is only one way to do DFS or DFS. So that means we are going to use your list as a reference as to how you do the DFS or DFS. Okay?